you lose complex differentiability of differentiable solutions. So this is a disadvantage. You have a gauge invariance, and that's what physicists love, and that's why they put in the absolute value psi squared. So today it is just psi squared. And in complex time, if I look in complex time, then these are two sides of the same medal, or perhaps perpendicular sides of the same cube, because in complex time, I can write these equations and they become the same. Except, of course, for Schrödinger equation, if I want to proceed in imaginary time, I better admit complex arguments, complex variables psi. Whereas in the heat equation, you thinking of U as something like temperature, we would think of U as real. So we have a U plus IV being psi, and we have a T equals R plus IS, real time, imaginary time, okay? And the two equations become the same. Now also, to have a definite problem, I impose Neumann boundary conditions on an interval, which for some reasons I take the half unit interval rather than the unit interval. The reason for taking the half interval with Neumann is I can reflect, and then I have period 1 of solutions in space X, but that's not a big deal. Let me do an example, and I apologize for such a PDE advanced seminar that I start with an ordinary differential equation. However, ordinary differential equations are the special case of spatially constant solutions. So let me look at these. And I take the equation W dot equals W squared minus 1. And there are explicit solutions, you can do separation of variables, and you see that the solution is, for example, a hyperbolic tangent and it shifts with complex arguments. Now, if you plot what happens in the UV plane, in the real and imaginary part, you see an equilibrium +1 and an equilibrium -1, of course. W dot equals 0 there. 1 turns out unstable, -1 turns out stable, and you get a solution, a real solution, U0, which decreases from +1 to -1. Very trivial. But in the complex, there are these other solutions which also decrease in a way from +1 to -1. They might increase a little bit. And all solutions are circles, by the way, for this. And if you just look at this picture and you draw the perpendicular lines, the orange curves, then this looks like electrical fields. And indeed, this is an explicit solution for the dipole field of a charge at +1 and a positive and a negative charge at -1, repelling a positively charged particle. Or it is fluid dynamics. It is, you have an incompressible fluid, incompressible irrotational fluid, and you pump in at +1 some water or something, and it comes out at -1. This doesn't mean I advocate fracking, but there are many potential applications. Or you can say this is a magnetic field. Put the Earth around this dipole, and you see the magnetic field in 2 dimensions of the Earth. Many applications, but what I want to point out is that the orange curves are actually the solutions in imaginary time. Why? Because the solution is analytic. So the map W must be analytic. Analytic maps preserve angles. So therefore, the analytic map from time to W, where I have real time and imaginary time, must map trajectories to orthogonal curves. Moreover, all these periodic orbits here have the same period. This is simply because real and imaginary flow have to commute. You don't have to, it obscures these things when you plug in a tangent, hyperbolic tangent, and calculate too much, you know. But just conceptually, it is clear that all the periodic orbits have the same period in imaginary time. Why? Because I can go, if I have one periodic orbit, say this one, then I can step backward in real time, for example, some time interval to reach this point, then solve in imaginary time, and these two flows have to commute. So if I first go around with a period and then imaginary period and then do a real time step, it must be the same as first doing the real time step and then going in imaginary time. Therefore, all periods have to be the same. Very easy. You can also do explicit solutions and invoke calculus of residues and so on. There are many ways to reach that. Now, as we pass to partial differential equations, let me warn you against some total confusion, some entire confusion. Namely, what does the word entire mean? Let us study real solutions. Here R is time of a real partial differential equation, and then we call such solutions eternal. So they are eternal in the sense that they exist from minus infinity to plus infinity, right, in time. I also require, when I talk about eternal solutions, the solutions to be uniformly bounded. Some people do not require that. I do. So we can talk about real eternal solutions. Unfortunately, some people call such solutions entire in PDE. Let me not do this today because I want to reserve the word entire for complex entire functions. For complex functions, which are complex globally in the complex plane. No poles, no singularities, no bounded domains of definitions, and so on. Okay, so a complex entire function is a globally convergent power series. All right. Now, Hannes Stuke pointed out that real eternal solutions, PDE solutions, can blow up in complex time, or perhaps should blow up in complex time. So if I have a real eternal solution, I should get suspicious and say, this is not going to be complex entire. Of course, there are trivial counterexamples. If I have a time-independent solution, it is eternal, and it is complex entire because it doesn't depend on time at all. Sorry for that. So let's forget about such trivial things. If I have a sine function is bounded in the real and is complex entire. So let's also forget about sines and cosines. So up to obvious counterexamples, I want to show you and prove to you that specifically in the equations that we looked at, real heteroclinic solutions for the nonlinear heat equation, real heteroclinic solutions, like from +1 to -1, come necessarily with blow up in imaginary time. So if you are very lazy and you seek a blow up solution for the Schrödinger equation, you just look for a real heteroclinic solution and automatically it will blow up in imaginary time. It will give you a blow up solution of the Schrödinger equation, linking the nonlinear versions that I'm looking at here. So here are a few references. Of course, in the ODE setting, Weierstrass triumphed by understanding that elliptic integrals, more precisely the inverse functions of elliptic integrals, were doubly periodic functions called elliptic functions, Weierstrass elliptic function. And they necessarily have to be meromorphic because if a function is doubly periodic in the complex plane, then it is bounded, the fundamental domain is compact, and therefore would have to be constant. Constant solutions are not interesting. Then there's the Pain-Levé hierarchy of 6 meromorphic types, second order equations, depending on time, which I denote Z here, which have non-movable poles, so poles in positions which do not depend on the initial condition. I will come to later work by Wittig and Ushiki, very interesting stuff, ODE stuff, which says, after all, certain ODEs do not have entire solutions at all. So if there are no entire solutions at all, then we don't have to prove anything. Then whatever solution we take, maybe non-constant solutions, it will automatically blow up. Here's the celebrated point of Masuda, 1982, how to circumvent real blow-up. That's what I started with. And there's work on blow-up shapes. I would like to point out work by Lee and Sinai on blow-up for complex three-dimensional Navier-Stokes equations. So the hope was to circumvent blow-up in Navier-Stokes, and then perhaps in the limit, also get global existence or something. It turned out a little different. This is open regions in complex 10-dimensional parameter space where they can show that solutions do blow up in finite time, but that's not the real 3D Navier-Stokes, of course. Now, Guo and others took real time and complex W, but they stayed with real time. Here, the monograph on real blow-up by Pavel Kvitner and Supple. Numerics, the dissertation by Hannes Stuke, which I mentioned in the beginning, and then some rigorous numerics, recent results by Jacquet and others, which I will show you. So what did Kyuya Masuda do? He circumvented blow-up, real blow-up for this equation by passing to complex time. However, when he joined, you can circumvent real-time blow-up time in the positive imaginary part and in the negative imaginary part. And these two solutions you can rejoin on the real axis, but they never agree, except in the spatially homogeneous case. Now, Cho and others comment, this is very nice. I think I want to read this to you. Masuda's pioneering work does not seem to have a follower in 2016, they write. His paper seems to be a good example of a paper of high originality with few citations. So don't believe in these citation indices, okay? High originality, few citations. This means there's a lot of space here to step in and work on in the field. There's still very few people. It seems to us, although there are numerous papers studying blow-up of solutions of nonlinear parabolic equations, few investigate singularities in the complex T-plane. So this monograph, for example, of I don't know how many 100 pages, 400 pages or something, has a very small paragraph on Masuda's work, and that's the only mention of complex time. So what is the abstract result? The abstract setting is complex analytic semigroup.
Okay, no, sorry. It seems like now the slide is still the same.
Yes, I see that.
You are now,
I have.
we are still at the references on blow up.
Yes, yes, I see that. It doesn't seem to react.
Yeah.
Can you kick me out of screen sharing and I start the screen sharing again?
Okay. You want to? Yeah. Okay. Yeah, please. So Alejandro, what can you see? Are you still? Now, yeah. Now it moves. Yes.
Now it moves, right?
Yeah. Now we can see the QR Masuda's. Yeah.
But now I go to full screen and it doesn't show.
It's full screen for me. Yeah.
Not for me. I can see the open apps in your iPad, but I cannot see the slides.
Now can you see the slides?
No.
No, I cannot.
Weird.
Now we see it again. Okay. Now I see it
Yeah.
again.
Now I see it. Yes.
Okay. There's a delay somehow. Yeah. Somehow. Yeah.
Now I don't see the speaker, the audience, but anyway, I have to, maybe I have to.
Yeah.
Yeah. So now the audience is gone, but it doesn't matter. Let me continue. That's why I
Okay,
never
yeah.
trust WebEx. I'm sorry. Okay.
We are here. We are
So-
here. Yeah. Sorry. Yeah.
So we have complex analytic semigroups and and you don't see my cursor. Very nice.
Yeah. We cannot see your cursor.
Yeah. Now
If you
here's the
allow,
cursor.
yeah. If you allow me,
So
I can discuss with the IT support.
We have a
Yeah.
very long delay now. We have a very long leg. So we have an
Yes,
analytic semigroup. And I just passed to the next page on my own screen. Aha, now I see. So
Yeah. I see the delay is very long somehow. I think we should solve the problem. Otherwise, the quality may not be good. Yeah.
okay,
Do-
let
okay,
me
so
just try.
maybe we
Okay,
can
complex
do a,
analytic semigroups. So I have a generator of an analytic semigroup, and I study this equation. I studied this. Now it works again. W dot is AW plus F of W, very general. And I assume, of course, complex entire F, real for real arguments. And I get analyticity, but only in complex sectors, you know, sectors opening to positive real part. And the point is that real and imaginary semiflows commute. You see, of course, I can study such an equation in real time. But what I forget then is that all these real-time solutions, they have a secret relation to each other because they are connected by a commuting flow in imaginary time. Okay. And let me point out that analytic unstable manifolds, local unstable manifolds are analytic. Now, the next important notion is non-resonance. And here I work in the analytic finite dimensional unstable manifold of a hyperbolic equilibrium. And non-resonant are the eigenvalues if I cannot write one of them as an integer combination of the others. Okay. This is what I call non-resonant up to exponential rate mu d. And why do I assume that? Because there is a wonderful theorem that's actually the dissertation thesis of Henri Poincaré, 1879, that if you have non-resonant eigenvalues, then you have local complex linearization. So this is, there exists a local holomorphic diffeomorphism, which commutes the nonlinear flow to its linearization. This is a very strong theorem, and a proof can be found in the beautiful book by Ilyashenko and Yakovenko. So non-resonance implies analytic linearization. And what does this mean for imaginary time? Well, if I have real eigenvalues, I have expressions like some exponential I mu k mu j s times coefficients Cj. I have a finite sum like that with real mu j. So this is a quasi-periodic function. This is a periodic function with several frequencies. Frequencies mu j. And local linearization means that for large negative real parts, I will shift time so that R star equals 0. For large negative real parts, I have this quasi-periodicity in imaginary time. Now, nobody knows what happens globally, of course. This is a local result. I cannot globally linearize the equation. Now, the first theorem is the following. I assume I have real hyperbolic equilibria here and here. So this is V, this is W. And for technical reasons, I have to assume W is attracting, strictly negative real part. And here is my heteroclinic orbit, gamma. Okay. And so this, I abbreviate this by this wavy line. In particular, this is an eternal solution. Now, if I have non-resonance at V with real unstable spectrum, then this heteroclinic solution can never be complex entire. More precisely, it cannot possess an complex analytic extension to the entire complex plane. So this generates blow-up. And let me prove this for you indirectly. So I assume that I have complex analytic, globally complex analytic solution, and I will lead this to a contradiction. What I'm plotting here is the time plane, R plus IS. And the blue solution is the heteroclinic orbit that we get from our whatever techniques we have. I will comment on such heteroclinic orbits later in detail. And the question is, can this extend to the entire complex plane? So suppose it does, then I can first solve in the imaginary, or second solve in imaginary time. So let's C be a bound on absolute, on norm of gamma for the real orbit. So on the real line, I have a sup of the norm. Because it's heteroclinic, it's globally bounded. It's an eternal solution. Now, if I look for negative real parts, then I can linearize. But if I linearize and I have negative real parts, the solution remains bounded. So this symbol, approximately up to 1 equal to V, means the difference to V is of norm 1, say, some fixed number. This means everything is bounded here on the left. Now, the idea, of course, is to reach a contradiction by proving that gamma is bounded everywhere, because a uniformly bounded complex analytic solution is constant by Liouville's theorem. So I have to show bounds everywhere. By the maximum principle, it is sufficient to show bounds on large rectangles, and that's what I will do. So I will now proceed to large imaginary parts at r equals 0, and I have quasi-periodicity. Now, quasi-periodicity implies that again and again, I'm getting arbitrarily close to this initial condition gamma 0 in imaginary time, just by quasi-periodicity. So I can get delta close to gamma 0, delta as small as I like. Now, if I'm very close to gamma 0, then the following happens. I have assumed W to be locally asymptotically stable. This is a proof in steps 0 to 7. I gave you the horizontal line. Now I cannot point, okay? But perhaps if Jayan points for me, I don't know.
Okay, I can. Yes. Can you see
So
my
the horizontal line, the R-axis, we have step 0. We have a bound on the heteroclinic orbit, of course. Then this is like Advent's calendar. Then on the left, step 1 is that the solution, because of quasi-periodicity, sorry, because of linearization, is close to V. And the distance, let's say, B1. Then we go up on the S-axis to Sn to infinity. We can be delta close for arbitrary delta. That's step 2. And in step 3, we go to the top where W is locally asymptotically stable. Being locally asymptotically stable means convergence, of course. Now I read the top line. The top line of the page. And if I start epsilon close to W, I remain one close forever after. And moreover, I converge. That's just the definition of local asymptotic stability. And therefore, if I can get any delta close to gamma 0, and gamma 0, of course, gets converges to W, then I can get epsilon close to W, and therefore I am bounded by C, the bound for gamma 0 plus 1 on the upper horizontal line, okay? On the entire blue upper horizontal line, all the way to the right. Now, in step 4, I say, what happens in between? Well, in between, so I fix that Sn now, arbitrarily large. Now I have a compact interval, imaginary interval from 0 to Sn. And on that compact interval, for any Wk, I mean, this is a finite imaginary time away from gamma 0, because real and imaginary flow commute, I can remain arbitrarily close to W, I can get epsilon close once and then remain one close to W forever after. That's step 5. In step 6, I point out that I can do this anywhere, and this is an open condition. So I have a small interval, S interval, where this works. I can take the maximum of the times I have to wait until I'm epsilon close and therefore one close. And that's step 6, which makes it uniform everywhere in this horizontal strip. And yes, and now on the boundary of this rectangle, what is the rectangle? Horizontal axis R, vertical axis S, and top Sn to the right and to the right as far as I like. I have boundedness. I have a uniform bound. The uniform bound is C plus 1. C does not depend on Sn. It comes only from the original heteroclinic orbit. So I have a uniform bound of gamma everywhere. Inside, by the maximum principle for complex functions, for complex analytic functions. So the assumption that gamma B entire leads to the conclusion by Liouville's theorem that gamma is constant. Now, constant functions are not good candidates for heteroclinic orbits. They are just equilibria. Okay. So of course we start with V different from W for a heteroclinic orbit. Next slide, please. Now let me pass to quadratic reaction diffusion equations, okay? And I am drawing a bifurcation diagram of these solutions, and these solutions can be calculated explicitly, and solutions do blow up in finite time, as already Masuda discussed for lambda equals 0. And I have several references here for people who study blow up and grow up and so on in these parabolic equations. Now, what I would like to point out is the line W0, the inclined lower line. That is a constant solution, minus square root lambda over 6, and W infinity plus square root lambda over 6. Now, the W0 solution is always stable, and that is the candidate for the target of the heteroclinic orbit. And the sources of the heteroclinic orbits are the W infinity and the W1, 2, 3, 4 bifurcating solutions. The funny vertical slope on of the blue curves on the horizontal axis is because I choose a funny scaling where everything is just integer multiples of a primary curve. I chose the 4th root of lambda to the right and the square root of W of 0 sine square root to the top. And now Jayan knows this, of course, extremely well, these bifurcation diagrams. And now the slide is gone.
Slide? Here?
Can
you see the slide?
I cannot see anything.
Huh? Yes. I can see the slide. I can
Yes,
see.
me too.
So Alejandro, can you see the slide?
Yes, I can see your pointer moving.
Yeah. And Bernold, can you see my slide?
No, now I cannot see anything.
Ah. Okay. Let me share again.
This is my bad day.
No problem. Can you see the slide again?
Oh, here, yeah. It disappeared onto a different screen. I can see everything. Okay, very good.
Okay.
Next slide, please. Yes. So here's the main theorem on, or are the main results on these Schrödinger and parabolic heat equation correspondences. So we consider a heteroclinic solution in this particular setting now, emanating with a fast rate, which I call mu d. So the eigenvalues are mu0, mu1 up to mu d. Okay. And there are several results. So I have to prove that gamma is non-resonant. This is a difficult condition to actually check because you have to check the spectrum, which is of course real, at a spatially non-homogeneous equilibrium. That is not an easy task, okay? So I have to check this integer non-resonance. And we managed to check this with Hannes Stuke in 3 cases. Namely, if the unstable dimension, the fast unstable dimension is not too large, is like 1 over square root of 270% of the unstable dimension, or if the unstable dimension is not more than 22. So there were some integer arithmetic, integer inequalities, numerical checking there, or symbolic checking. And for the homogeneous solution, it always works, except for a discrete set of lambda, which in the case of the homogeneous solution may accumulate at the bifurcation points, does in fact accumulate at the bifurcation points. So with this finitely many, locally finitely many, or a discrete set accumulating at bifurcation points of exceptions, the following holds true. These gammas are resonant. They are not complex entire by the theorem which we proved in public with interruptions. And the solution experiences Schrödinger blow-up at finite time. For some, initial conditions are 0. So along the heteroclinic orbit, there are initial conditions, R0, where you experience finite blow-up in imaginary time. Certainly, if R0 is very negative, you cannot expect this blow-up to occur, okay? Because there it's quasi-periodic. Next slide, please. Now, non-resonance. The results we use are on Weierstrass functions. And I give some literature on the right, and I can only warn you the literature is a complete mess. Everybody says, oh, this is beautiful theory, and there are expansions. And we expand with respect to the Weierstrass parameter tau. I said these equilibria are, from the complex analysis viewpoint, elliptic functions. And the elliptic functions have a double periodicity in the complex plane. And there is a lattice parameter tau. The horizontal period is 1. That's why we chose an interval of length half with Neumann boundary conditions to fix the standard notation of period 1. And the other lattice period is tau with non-negative imaginary part. So this is a lattice parameter. And then since there is a periodicity, actually the way I wrote it, a periodicity of 2 rather than 1 in standard theory, I can Fourier expand with respect to h is exponential pi I tau. And what you see here are the Fourier expansions. You have Fourier expansions for the global Fourier expansions for the Weierstrass functions and for the associated parameters, except these complex analysis guys, they never write this in terms of bifurcation theory. Okay, you have to translate. These fields diverged from each other approximately almost 100 years ago, and now you want to stitch this together again, and it is possible. And this way you get expansions, explicit expansions, step by step. I don't have an expansion to infinite order for the eigenvalues. And this is case one is mostly, so this is when J is not half the unstable dimension that we are looking at. And then there's the other case where J is half the dimension. And you see expansions with respect to H up to order H squared. Now, these are analytic functions. And when can a resonance occur? Well, it either occurs at discrete points, because resonance is a relation between integer relation between different mu j. Yeah? So this either happens at discrete points or the thing is identically equal. So by comparing the coefficients, you get a question whether integer combinations of 24n squared, 11n squared plus 4j squared divided by n squared minus 4j squared, whether these rational numbers can have integer relations. That's also an intriguing question. And we were only able to do this up to n equals 22 to assert that there are no such relations. Okay. Of course, when you get more n and j varies from 0 to n, then you get more possibilities, and it becomes computationally quite interesting to solve these, in principle, trivial Diophantine equations, but not so trivial if you plug everything in. Okay. Next slide, please. Now, I would also like to mention that we only study real equilibria, but they are complex equilibria. So the theorem, of course, would also apply to complex equilibria. We have not studied those. They are interesting lattice questions, which for reasons of time, I will skip now. Next slide, please. So this is work by Jonathan Jacquet and co-authors, where you see specific Weierstrass functions. They actually calculated this with rigorous numerics, but it can be done explicitly, as I give the explicit expression in the lower line. They did this like with verified numerics. And on the next slide, you see the beginning of unstable manifolds of these. Next slide, please. Yes. So in real and imaginary parts, real part is blue, imaginary part is red, and they find heteroclinic orbits in the Schrödinger equation, heteroclinic orbits between these psi's and the trivial solution. And because the Schrödinger equation, unlike the heat equation, is time reversible, you get heteroclinic loops in this way. Okay. So this is something we did not do, because I do not have the analytic means yet to study heteroclinic solutions for Schrödinger equations. No zero number property and so on, for which Alejandro would be specialist in the real case and in delay equations. Next slide, please. Now I have ventured on a detailed analysis of what happens with nonlinearities of higher degrees. And I have shown degree 3 and 4 for ODEs here. And the blow up is, so the second and the fourth picture, can you point at those? Picture 2 and 4, they show in a view with infinity in the center. And the blow-up orbits are indicated in red, So the orbits which go to infinity in finite time. And blue are blow down orbits. They come from infinity and return to equilibria. However, if you now try, so on the left, it's the same picture, except you have a circle at infinity. So the outer circle, this is the point infinity. And there are alternating saddles and sinks. This is called Poincaré compactification of the plane, which precisely describe the blow up and the blow down orbits in the ODE case as stable and unstable manifolds of saddles at the boundary. And these are the red orbits. So the red orbits in the left picture are the same as the saddle orbits in the second picture. And what you see there is that circumventing blowup doesn't work at all. Because if you look at the left picture and the orbit plus I epsilon, which goes to the top equilibrium, and minus I epsilon, these are small perturbations of the original blowup orbit, but they end up at completely different equilibria. So there is no joining of solutions after blowup. This blowup phenomenon that Masuda observed is a peculiarity of quadratic nonlinearities only, because in the quadratic case, you see all quadratic ODEs are in fact linear. Because the quadratic ODE is invariant in the class of quadratic ODEs is invariant under the action of the Möbius group, the fractional linear transformation of the unit sphere. You check this by translation is trivial and scaling is trivial, and you check this by substituting 1 over W as new variable. It is quadratic again. Therefore, you can transform any quadratic equation to one which has a 0 at 0 and a 0 at infinity. These are the linear equations. So any quadratic equation, ODE, is actually linear from scalar from the complex viewpoint. That's why this hyperbolic tangent works and why these addition theorems for trigonometric functions work, and et cetera, et cetera. Next slide, please. Let me skip some details here. Next slide. Because time has, yes. So then I studied the case W dot ODEs is a function of W, and I studied polynomials with simple zeros E0 to ED minus 1. So D is the degree of the polynomial. And then if you define eta as 1 over F prime, 1 over the linearization at equilibria, then these eta can be prescribed arbitrarily. This is not a standard interpolation. So the last line on this slide is there exist polynomials F with prescribed derivatives at their zeros. I have these zeros. I prescribe all the derivatives, but I cannot prescribe where the zeros are. You are familiar, of course, with Lagrange interpolation, Hermite interpolation, and generalizations of that, okay? But this is not a standard interpolation problem because I'm given eta j, and I have to solve for ej. This is an ODE talk, which I can give at another time. But there is a constraint. These reciprocal derivatives have to sum up to 0. This is simply because these are the residues of 1 over F. And if I take a large loop enclosing all equilibria, I can retract this loop to infinity, where 1 over F is integrable, and therefore the residues must add up to 0. And I assume that for subsets, the sum is never 0. Okay. I don't know how to prove this without this assumption. I have examples where this assumption is violated, but this is a technical assumption I need. Next slide. So you can prescribe derivatives That is, you can prescribe the linearizations everywhere. You just don't know where the equilibria sit. But you know who is a source and who is a sink and who is a Hopf and whatnot. Okay. Now, the next two theorems are extremely recent, as Jayan knows. It talks about the connection graphs of Poincare compactifications. Poincare compactifications are the things with the circle at infinity as indicating infinity in the disk. And I have to assume in purple, magenta, third line, counting the headline, no, magenta, assume sum of real eta j non-zero.
Assume.
It's below the equation here, yeah. So this assumption excludes Hopf centers. It is not allowed a purely imaginary eta j or f prime at an equilibrium. So all equilibria, finite equilibria, are hyperbolic. They are either sources or sinks because we are in complex dynamics. But it also excludes heteroclinic connections between boundary saddles. So under this assumption, a generic assumption certainly, because we can prescribe eta j arbitrarily, I can draw the connection graph of the Poincare compactification in the interior. Like I have sources and I have sinks and I have heteroclinic orbits between them, and the connection graph draws an edge between such two vertices, equilibrium vertices, if and only if there exists a heteroclinic orbit. And these connection graphs are trees. They are planar trees, and there is a one-to-one correspondence between these Poincare compactifications and the planar trees. Any planar trees with D vertices, of course. And the final theorem in this classification says all planar trees arise as connection graphs. So now, talking about the dynamics of the scalar ODE is as easy as drawing graphs. Next slide. I'm finishing quickly now. I'm sorry for going over time. Here's an example of the 14 planar trees with 7 vertices. So I drew these by hand. And I also did this for 8 vertices where there are a few more. And then I looked up the sequence of integers which appears. And next slide. So online encyclopedia of integer sequences here. It is sequence number 2995. And it classifies the planar trees up to orientation preserving equivalence, which is the same as handshakes. So if you have seven vertices, you can seat 2 times 6 friends around a table and ask them to shake hands. Now, they should shake only one hand, not both, okay? So one hand goes to the back and you shake hands, but the handshake should be simultaneously and not crossing each other. That's the orange curves. And the handshakes are equivalent to the planar trees. And if you further abstract the handshakes, you can also talk about simple circle chords. So you take a circle, equidistant points, 12 points in this case on the boundary, and you draw the straight lines. So these diagrams correspond one-to-one to the trees, and the trees are one-to-one the connection graphs of the global compactified dynamics there. Next slide. And there is even a formula which clever people in combinatorics have done in 1972 about the number of such handshakes. And the next slide. So this is the first few numbers, and experimentally I went up to 35. Then I looked up whether that sequence was known, and then there's a lot of work, of course, to have to prove the theorems that this is actually the ODE dynamics. And this is just the ODEs. I think we can go to the summary slide now. I will skip the ultra exponential and so on. So what have we done? We have tried to work out an example of the Hannes Stucke paradigm, how real eternal contradicts complex entire. We have seen how specifically how non-resonant heteroclinic orbits to stable equilibria are not complex entire. We have used that to draw conclusions on quadratic Schrödinger blowup from heteroclinic parabolic orbits. And I have indicated a classification of even the scalar ODE flows, the simplest interesting case. For approximately 15 years, I have told my students working on blowup that they should study the simplest interesting case, which would be the ODE. Nobody listened. So in the end, when you are retired, you have time to do all the things you told other people to do and try them yourself. And I would like to remind you that meanwhile, there's a 1,000 euro prize, which I offered personally from my own pocket to construct a complex entire real homoclinic orbit in any ODE. Thank you very much. The challenge is still open. Thank you very much. Sorry for going over time and for the technical.
Thank you. Yeah.
Next time I will let you do this. It works much better.
Okay. Should I still share the screen or I quit? I stop sharing. Can you see me? No.
I think sharing is okay in case there are questions.
Sharing. Okay. So thank you very much, Bernold. Today we have a very unusual talk, and not only is this a technical problem, but also we have a 1,000 euro. Euro is not Taiwan dollar, okay? It's euro.
No.
It's a euro.
This is European euros, okay?
Yeah, European. I emphasize it's not Taiwan dollar, okay? It's not Taiwan dollar, okay? So example, and if you are interested in this one, of course, you can go to read the archive paper. And
so there are 3 papers on archive, and they all explain this, and one has a detailed explanation. But I talked about this challenge before, except at the time I talked about it in Taiwan, in your seminar, I think I was not yet courageous enough to put a 1,000 euro prize to decide, either give an example or prove it cannot happen.
Yeah. Okay, so I think now we can have some time to discuss and ask question, counter example, for example, okay?
Yes.
Remark and question. Just unmute your microphone and I will keep sharing the screen and you can indicate me which slides you want to check, please. But I cannot see any of you, okay? So I cannot see a name, I cannot see any of you, so please indicate. For example, Alejandro, you can help me, okay?
Or just speak. I mean, can you unmute everybody?
If I start sharing screen like this, then I say, where is
Can
somebody
unmute?
I think I cannot do so unless I start sharing. But Alejandro, you are the co-host. Are you a co-host? Huh?
I don't know if I am, but I can see all the people at the same time.
Maybe now please host. And now I am responsible for the slides. Yeah.
Okay. But anyone can unmute themselves, right?
Yes.
So, I mean, if there are no questions from the audience, then I will ask myself.
Sure.
Regarding the non-resonance, the conditions for non-resonance that you gave, I understand that non-resonance is necessary for the local description of the dynamics, right? The heteroclinic, essentially, along the heteroclinic.
Yes. It is a technical condition without which I cannot do anything, yes.
Yes, but still the result on complex time blowup may hold
Yes.
even without non-resonance, right?
Yes.
If I understand correctly.
Yes. Yes.
It's just that there is no technique that we know of.
Exactly. So at the moment, the obstacle is technical, and I just don't know. Okay.
I mean, unless one imposes some ridiculous condition like locally the dynamics look like this or something like that. Yeah. I see.
But you see, this will be very difficult to check numerically because slightest perturbation makes it non-resonant.
Yes.
I mean, really, I believe also this restriction n less equal 22, this is ridiculous. I mean, beyond that, simply the Diophantine checking collapsed. Okay, I never got a result. I mean, I think I let this run for a day or so, and for n equals 23, and there was nothing. And then I said, okay, fine, so be it. But we used only an expansion up to quadratic order. I do not know spectral Fourier type expansion like I did there in terms of the lattice. Fourier type expansion to arbitrary order. These guys were fantastic, you see. I mean, this is results which came up first in Weierstrass lectures. These expansions, and then Fricke writes a long book in 1916. Except they never look at it from this PDE point of view. So linearization and resonances were not natural questions at the time.
Yes.
Because the PDE framework was missing to even find these questions interesting. But they gave the complete Fourier expansions for the Weierstrass functions, for the parameters at which they occur in our language. And all that. One just has to translate, you know. This is amazing achievements. You know, they have formulas for all that. And then I only went to, I felt like a dwarf compared to these giants, you know. I mean, expanding to second order, Hannes can confirm this maybe. This was what the precise expansion was a dispute to almost to the end until we submitted this to archive, right? And for publication. So we got different results and so on. And the literature is partial, you know. I mean, some do this and some do that, and everybody does what looks very elegant, and terrible.
Yes. And of course,
and there are errors too in the literature. Okay, so you have to correct those. Sorry.
Yes, Hannes?
Yeah, so I have a question. I try to remember what I did, but so for me, the possibility that the two orbits coincide after blow-up were related to the linearization of the fast stable eigenvalue with which the heteroclinic comes in. So if you have a heteroclinic orbit, and then like in this easy case in the quadratic easy case, then on the other side you have a blow-up orbit, and the ability to join or to circumvent to join those orbits was related to the linearization and to the eigenvalues, because if the eigenvalues are not the same or not resonant, then you can circle around one equilibrium and circle around on the other side, and you can show that, like, okay, it's not possible that you get like a solution that is real on both sides again on the real time axis. And my question is this related to the ability, or can one see locally the ability to circumvent the blow up or not, what you have shown by analyzing the global or the compactified equation? Is there any local result that would tell you already, okay, this kind of orbits I cannot, this kind of blow up I cannot circumvent because it would connect equilibria with linearizations that does not fit? Or is it like a really honest result of the blow up dynamics? Because like
No.
what I always was doing is like I didn't study the blow up. I only studied the complement, so to speak. And so my question is there also a complement that would only look at the bounded results?
So questions by co-authors are always particularly tricky, but also go back to the co-authors themselves. But let me at least try to comment. So what Masuda proved was that only spatially homogeneous solutions of the purely quadratic PDE recombine after blow-up to the same solution. Now, in your language, this would say, what is, so you are generalizing that. What is the meaning of spatially homogeneous? You would say it is the incoming, it's the incoming speed or the outgoing speed. Now, for the outgoing speed, the fastest, indeed, in this parabolic equation, the fastest, the one-dimensional fastest unstable manifold is homogeneous because the first eigenvalue is homogeneous at homogeneous equilibrium. Now, the inhomogeneous equilibria do not appear in the Masuda setting. Okay. On the stable side, however, any generic solution, anything which is not coming in fast into a homogeneous target, will be asymptotic to mu0, to stable mu0. Anything, or up to codimension 1, anything. And this means that there is nothing, there is no characterization like fastest on the stable side. There are always the other eigenvalues mixed in. And I think that these other eigenvalues would play a role. The problem at the target is murky, is not very transparent because of lack of linearization. So this goes back to the technical question of Jaya. How important is this, of Alejandro, how important is this linearization? If we want to make progress on the PDE side, we have to get rid of this linearization argument, because in the stable manifold, being infinite dimensional, we simply cannot linearize. I know Shuini Chao tried very hard to linearize ut equals uxx plus a of x times u. So the linear parabolic version. And that never worked. I mean, I'm not sure whether he got any results or very complicated and unwieldy results, but that was C0 linearization, and we are talking about analyticity here. So, so I'm really stuck to overcome the central condition which Alejandro pointed out, the non-resonance. Okay. And you are thinking in terms of resonance and non-resonance. But even if you can linearize, you know, what do you do with the other terms? Now, the closest I got to your idea of fitting resonances or non-resonances at source and target was the ODE case, in which you can linearize, and there is a funny situation where if you assume global analyticity, certain Fourier coefficients of the quasi-periodic expansion in imaginary time would have to match. You can continue the coefficients even though the series stops converging. Okay? But on the level of coefficients, you can compare source and target. And so that's That's a point which would work out in the non-resonant ODE case. That's the closest I got, and yeah, any idea is welcome.
I also have more questions, but I don't know whether anybody else in the audience.
Well, I can stay on to discuss.
Maybe before asking more technical detail, let me ask a very naive question for for Taiwanese, for me. But why do we consider complex time? It's not physical, right? We cannot experience that. Then what's the reason to study complex
Now,
time?
if you look at the papers of Jacquet and others, they are quoted in the archive paper. Then they contend that. They give references from the physics literature, not exactly from Schrödinger, where they studied complex models away from the gauge invariance. So I would not say that. Secondly, I mean, the quadratic model has been so perhaps I should one of the references, if you go to the references page. Yes. So there is Cho and others. But no, Zhongsheng Guo, 2013. So Eiji Yanagida is also a co-author of this paper. So they study these equations in real time, but for complex W. For complex W, you can decompose into real and imaginary part, and you get particular, like I did for the ODE, and you get a parabolic equation, ut equals uxx, and then plus u squared minus v squared, and you get vt equals vxx minus uv. So you can study this as any quadratic, I don't know, reaction system or interaction system of populations, etc., etc. Okay. However, and they do that. Okay. So they say, we have equal diffusion in U and V, which is good. It gives us more comparison maximum principles and so on and so forth. Okay. And then they study certain solutions for that. And this is perfectly fine, but it forgets an important point, namely that all these real solutions commute with another flow or semi-flow. These are not standalone, solipsistic Leibnizian monads, which circle around themselves, but they are hand in hand with all their complex siblings. They come in families. On the other hand, there is the study of complex foliation, like Brazilian school and so on, and the complex foliation people, they forget that for our PDEs, time is a very specific thing. I mean, for the heat equation, real time is real time. And for the Schrödinger equation, this what I call imaginary time is also real time, okay? But I just warn against forgetting this beautiful structure which links the real and the complex. And I want to strongly advertise for that. Of course, we will have many systems of two equations with equal diffusion and quadratic right-hand side, which do not fall in, or cubic right-hand side, which do not fall into the same category of complex structure. But we have many differential equations which are not planar, and still Poincaré-Bendixson theorems are important. And some people even think they are important in in delay equations and other systems which are much higher dimensional. Okay. So therefore, it is, in my opinion, for scientific curiosity, not admissible to ignore a huge body of work in complex analysis just because that body of work has become incomprehensible to me. Moving away from differential equations, practically completely. And that's why I praise the book by Ilyashenko, and this is references on blow-up, but the book by Ilyashenko and Yakovenko so much, which, although with a strong interest in Hilbert's 16th problem on polynomial vector fields, real vector fields in the plane, going to the complex and hoping for enlightenment, which revives that theory. That theory has died out in Germany for terrible historical reasons. The reasons being that it was very strong, based on Weierstrass and other people, Riemann and so on, and then got abused or got mixed up with Nazi tendencies, not tendencies, but violently politicized mathematics in Nazi times by people like Teichmüller and Bieberbach, who, well, Teichmüller died in the war, and Bieberbach was shunned after World War II, and the tradition to study differential equations in complex time in Germany has effectively died out. So that's why I'm so much the more grateful that our Jewish friends kept up the tradition.
Okay. Yeah. Thank you.
But also, yes, in that sense, there is somehow a language missing, right? Because when we talk about heteroclinics and homoclinic orbits and so on, we do it from the perspective of the action of a real group, right? And then we have an ordering, and then we talk about omega limit sets and alpha limit sets and so on. But it's always been very unclear to me what's a homoclinic when you put it in the complex picture, right? What makes it special? What should be the defining feature that somehow induces this additional complex structure via these theorems by Hannes, right? What makes a heteroclinic connection so special in complex time that when you look at the whole thing, there has to be blow up somehow?
Well, first of all, it is difficult to establish blow-up in imaginary time, in these Schrödinger type equations. I mean, when you look, what these guys did was they did computer-assisted proof in finite Fourier spaces. Okay. And so far, the Schrödinger blow-up, like Cho and others, this was numerics, right? That was conjectural. Lee and Sinai, they prove things, and so this is, mathematically speaking, a difficult problem.
Yes.
And I found it very surprising, learning from Hannes, how he thinks that, so he told me many times how blow up and heteroclinicity are two sides of the same metal, even in the real case. Can you show this slide with the d equals 3, d equals 4 phase planes with the yes, okay. So here I'm showing real things, And if you look at the d equals 4 example, or the d equals 2 even is good for that, you see from E0 on the right, you see a blow-up trajectory. So this is the equilibrium plus 1. And there's a heteroclinic orbit to the sink E2 on the left. Okay, this is all real. And there's a blow down orbit to E2. Now, it takes a vision like Hannes has to say, no, these are the same thing. You only have to pass to complex time. Okay? This is an amazing insight in the real. I mean, let's look at complex numbers. What are complex numbers good for? Nothing at all, right? I mean, but suddenly you use complex numbers to evaluate real integrals. So there are conclusions in the reals which you can do by this detour. Or, I mean, Martin Fett was always advertising non-standard analysis with a similar argument. He said, well, if you take standard theorems, so theorems which make sense in standard analysis terms, and you have a non-standard analysis proof for them, then they remain valid in the real, in the standard analysis sense. Okay. So non-standard proofs can prove standard things. Complex proofs can prove real statements.
I agree.
Now I'm going to venture in 3 weeks to talk to our students at our department. They asked me to give a talk, and I gave them several titles, and they chose a title, "Is real time really real?" And well, now I have to think what to say, okay? But it is not even clear whether our real time is really real. It could be discrete, for example. Or if you ask Nietzsche, time itself could be a circle. Well, he is against it, but he only knows straight line and circle. Or if you go back to Thomas Aquinas, he, medieval 13th century theologian, he thought of time as two-dimensional, where our real time, the time we live in, is like along a circle from alpha to omega, but God is in the center, and he has the simultaneous perspective of all the circles where we have before and after. But in a way, the non-ordering of complex time, which Alejandro complained about, he saw as a practically divine advantage. So shouldn't we catch up with Thomas Aquinas?
You kind of used disadvantage all of the time, right?
Excuse me?
You kind of use disadvantage all of the time by going along the imaginary line, and then
Yes, yeah. Exactly. Yeah.
Also, I think that Hawking once talked about imaginary time when approaching the Big Bang. And there are proofs, I think, in quantum mechanics that like the tunneling probability is related to complex time detours of the ORI approximation, I think. But I also want to ask maybe
if you have a reference,
question.
please provide, okay, by email. Yeah.
No, I also have I have another question which is a bit related. I was always wondering, because also Jar asked like what do we learn from this? And my question is, do you think that the complex time blow up has a different phenomena or a different reason or different dynamics than the real time? So if I know the complex time, is it like pretty similar, or they're completely new phenomena? Like, I don't know. go into its actually system, and then like you have other things like how's it this bifurcations and this what is this diffusion induced bifurcations, how are they named again? Anyways, like my question is the dynamics of the blow up of the complex one, is it the same as the dynamics of the real one, or are there fundamental differences? And I'm asking this, for example, if you have an equation, a PDE, which has a blow up, but let's say not in the soup norm, and you have like blow up because like, I don't know, H1 norm or H2 norm or so gets unbounded. The idea was always like to use kind of the bounded part to prove blow up, because like blow up was too complicated. So let's study the bounded solutions where you can even do a CAP proof of heteroclinics if you want. And my question is, okay, I do a CAP proof, I have a finite dimensional approximation. There must be something in the ODE, if you want to have blow up, then something must go to infinity. Can one see, for example, the blow-ups that occur due to H1 or H2 norm blow-up? Or is it like a pure complex phenomenon that you then always have a subnorm blow-up or whatever?
Well, in our paper, there is a small paragraph on H1 versus L infinity, okay?
Yeah.
Of course, L infinity blow-up implies H1 blow-up, but H1 blow-up is natural in our setting. That's what we actually get for the Schrödinger, and then you have to conclude L infinity. In that case, you get away cheaply. But let me caution against what we actually know, which is extremely little. Now, what we actually know is that solutions are not entire. What we actually know is that for some R0, the solution blows up in finite time. We do not know whether this is a singularity. In the setting of your thesis, I don't have to remind you, the trailing slit in the domain before reunification or before at least return to the real axis happens has not been diminished. Even in the ODE case, we do not know whether this is a singularity. Maybe there's a chance to prove that it cannot be a meromorphic singularity. Okay, so if it is a singularity, it would have to be essential. Bye-bye. Bye-bye, Yukihiko.
Bye.
And so this is, and of course, finite dimensional approximation, I don't have anything. But you see, in the real case, we have two tools on which everything is based: comparison or maximum principle and variational principle. Both tools disappear in the complex. Maybe some vestiges remain, you know, the windshield wiper comparison principles and so on. But it is good to ask the questions, and it is, well, of course, I'm trying to assist in restarting this complex PDE business, but we are comparing first glimpses of an unknown world where everything is tabula rasa, you know, practically no results. I mean, what I present you, this is nothing. I mean, imagine the ODEs where all solutions, we are told, are explicitly known by separation of variables. How often have I done this separation of variables in class? And each time I thought, and everything is done, there is no interesting question there. I thought it would be something for my dear students to go home and tell me next week, this is all trivial. I have been struggling very hard on the ODE case. very hard, you know. And there are still lots of things I don't understand. And it's not only, I mean, also the combinatorics. I have eliminated the symmetric parts. So can we classify planar graphs up to orientation preserving homeomorphism? No, up to homeomorphism. So I calculated the numbers. They are nowhere found in the on-sign encyclopedia. Okay. It's a different, this is very basic things. So little known and so little time.
Yeah.
Now you are asking questions far beyond that is totally acceptable. Now to reach presentable results, we have to bridge the gap and then be rightly disappointed at how little we achieved.
Yeah. That's true. Yeah.
So science can teach humility too.